All right, enjoy listening to this episode of Equestria Girls in the background. I know I will. I'm going to take a look at some more fully fleshed out versions of drag forces in physics. These kind of go beyond what you need to do on the exam, but maybe you're interested. Some of you have been hankering all year, I know, to have to deal with air resistance and problems. Probably the simplest version of this is just like a ball fired into a big old block of ballistic gel or something like that. So this block's got some initial velocity. Hold on a second. I gotta go figure out what the heck's going on in the other room. Just clearing off the piano so she can play along. Okay, so ball fired into this ballistics gel. It's got some initial velocity before it hits the gel. And then a velocity-dependent drag force is going to slow it down. So we're just going to worry about that part of the free body diagram. But you would have, that sounds almost musical. But it's got some initial velocity, and then here's the drag force. And let's just say that is negative BV. Negative because the force is directed opposite the velocity. And then B, if you read in the textbook, like B is just an amalgamation of all the different constants that feed into this. We're just calling it B, so we don't have to track four things while we're working through this. All right. So if that's the force responsible for slowing this thing down, we're not going to worry much about the other forces. We'll just call that the FU. That would equal the mass times the acceleration. So quickly we can get an expression for the acceleration. It's going to be negative BV over M. And certainly there'll be situations where this could be quadratic, where it would vary with the square of the velocity, but here we're just doing linear. So we're going to take this, and this would be in the AP exam where they would say set up but don't solve a partial differential equation. And that's because the equation for the acceleration includes velocity, and they kind of feed back on each other. Like the velocity that we have affects the amount of acceleration that it's going to be experiencing. So recall that acceleration is the change in velocity over the change in time. Calculus world, that's dv dt. I'll write that as negative bv over m. And then we're just going to get the velocity stuff over on one side. So this is going to become dv over v equals negative b over m t. So, not t, dt. Sorry. I've got the Jaws theme going in the background. So that's where we're at right now. Okay, so then we got to think about the bounds of integration, and this really matters here because it's not just going to default to 0 to v. This thing doesn't start at 0; it starts off at a velocity v naught, and we don't want to take it to 0. We're going to take it to v. Okay, some later value. And then likewise over on the other side, we got to think about how this goes. This is going to run from time 0 to time t. Okay. The right side of this is pretty straightforward. Negative bm is a constant, so we can pull that out in front of the integral. So negative b over m. And then effectively in here right now is 1 t to the 0. Okay, so where we're going to land with that is when we do the antiderivative, we're going to increase the exponent here, so 0 plus 1, and then we're going to divide by that 0 plus 1. So this would be 1 times t to the first over 1, so this becomes t inside. So we end up with negative b over m t, and again we're going to evaluate that from 0 to t, so that's just going to become negative bmt. Okay, b over m t. All right, What's happening over on the left side, though, is a little more complicated because this v is on the bottom. So that's 1 over v, which is the same thing as v to the negative 1. And if you recall in the calc equations, it says, hey, this power rule in reverse thing works just great so long as n is not equal to negative 1. So what the heck do we do? Well, this would be problematic because if we tried to apply the power rule in reverse, I'm going to have v to the negative 1 plus 1. And then this is going to get divided by negative 1 plus 1. So I'm going to end up with v to the 0. Okay, that's 1. Ooh, but then I'm dividing by 0, and that doesn't work. So math says that when you have something to the negative first power, then that antiderivative is going to be the natural log of that thing. So 1 over x dx, that becomes the natural log of x. So in our case, we've got from v naught to v, we've got 1 over v dv. And so that's going to become the natural log of v, and we want to evaluate that from v naught to v. So that's going to be the natural log of v minus the natural log of v naught. Okay, and so then there's another math thing that we need to be aware of, and you can check this on your calculator. But if you have the natural log of a minus the natural log of b, that is equivalent to the natural log of a over b. Okay, and so this is going to become the natural log of v over v naught. All right, so that's what's happening on the left side. So if I join everything back up again, we've got the natural log of v over v naught equal to negative b over mt. All right, you can see why they don't have you do this on the exam, at least not write everything out in steps, because this is just kind of time consuming. So how do we get v by itself? Well, we got to get rid of this natural log thing, and we do that by taking e to the natural log of v over v naught, and then that's fine as long as we do the same thing on the other side. And these are kind of inverse functions here. So e to the natural log of v over v naught becomes v over v naught. V naught is, again, the initial velocity. And then on the other side, we have e to the negative bm over t, okay, because that's what that is. It doesn't go anywhere from there. So now I've got my expression for the velocity as a function of time. Velocity equals v naught times e to the negative bm over t. All right, let me pause for a second so I get a drink. All right, so now we have the velocity as a function of time. We have an expression for the acceleration, but if we want the acceleration as a function of time, because that acceleration is going to change in time, then we can say acceleration equals dv dt, and then we want the derivative of this expression we got for the velocity as a function of time, and v naught's a constant, so we have e to the negative bmt, so we've got to take the derivative of the inside, okay? So that's going to be negative bmt to the first. The derivative of that with respect to time is going to be just negative b over m. So that gets pulled down out in front, and you get negative b over m v naught times e to the negative b over mt. Okay, at time 0, then the acceleration is just going to be so at time 0 this becomes 1 effectively, and so the acceleration initially is negative b over m times v naught. That was what we had up above. So we're good there. And then the one you really never will expect to see on the exam would be to find the displacement there. So we have our expression for the velocity. Velocity is the derivative of position with respect to time. So that is v naught e to the negative b over m t. And we kind of separate this out here a little bit. And set up our bounds of integration. This is going to go from 0 to x. We're just saying it starts at position 0 because it doesn't tell us anything else. And this is we're integrating with respect to time, so it's going to run from 0 to t. And on the left side, again, effectively, that is 1 times x to the 0 dx. And so the integral of that is just going to be x. Boop. And then over on this side, so we're going to do the antiderivative of this stuff here. V naught's a constant again, so we don't really have to worry about that. But antiderivatives involving e to the x. So again, this was discussed in the calculus givens video, so go back and check that. But when you're doing the antiderivative of e to the something, you got to recognize what is that current function the derivative of. And so this ends up becoming the opposite. Oh boy, what's going on here? We're going to pull down the constant up here and run that into the denominator. So that's why it's going to be flipped here. So it's going to be opposite of m over b times v naught. And then, oops, that's times e to the negative b over m times t. And again, that's going to run from 0 to t. So negative m over b v naught e to the negative b over m t minus negative m over b v naught e to the negative b over m times 0. Because again, I'm going to go final minus initial more or less here. E to the 0 is 1. So this is going to become negative m over b v naught. I'm subtracting negative m over b v naught. So that's the same thing as adding m over b v naught. And then this is negative over here, m over b v naught times e to the negative b over m t. Okay, that equals x. And I can just clean that up a little bit here. Let's see, this is going to factor out m over b v naught, and then this becomes 1 minus e to the negative b over m t. All right, that is equal to x. Let me just double check there real quick. I think that's where we landed. All right. All right. And so then if we just take a quick look at what happens here as time goes towards infinity. So for greater values of t, this is going to approach 0. So everything inside the parentheses approaches 1. So sort of your ultimate, let's see, e to the negative b over m t approaches 0, and x is going to tend towards m over b v naught. So that would be like the total displacement stopping. All right. So that's that. We've got position as a function of time, acceleration as a function of time, And velocity as a function of time is up here somewhere. There we go. And that is why you don't need to do all that on an exam. That took me about 15 minutes right there. And they know you don't have time for that on exam day. And so I'm going to shut up so this thing will be uploadable.